So if there is destruction, there goes something wrong, isn't it?
Well, with autoimmunity, there goes something wrong, but destruction is not necessarily.
That's true. They have, in development, you also have destruction because of apoptosis, for instance. But there is at least, and that is something you should realize, there is at least a component of the immune system that reacts with self. And is this about the innate or the adaptive immune system? It's about the adaptive immune system. So if you talk about immunity, being immune for something, for a pathogen, it's about the adaptive immune system. The innate immune system is of course involved, but it's the adaptive immune system that makes you immune. So it's also the adaptive immune system that makes you autoimmune. What does it mean if you have an autoimmune disease? No idea? Yeah?
Chronic inflammation.
It's chronic inflammation. Inflammation, is that because of the innate or the adaptive immune system? It's innate.
But doesn't the adaptive immune system activate the innate also?
Yeah, it's anyway, it's a distinction, innate, adaptive, which is quite subjective in a way, because we like to put things in boxes. And there is always crosstalk between innate and adaptive. I fully agree with you on that. Basically, the immune system always starts with the innate system, then goes to the adaptive, and then it's crisscrossing all over the time. That's true. But basically, in autoimmune diseases, well, let's put it first. If you have autoimmunity, it means that your adaptive immune system has components reacting with self, with your own body. Whether it's destruction or not, it doesn't matter. Anybody of us has autoimmunity. If not, you would not survive. So autoimmunity as such is a physiological phenomenon. That's good to keep in your mind. However, in some cases it goes wrong and it becomes detrimental, and then you get a disease. So the destruction goes beyond as what you want to have, and there are complete tissues or organs destructed, like in diabetes, where the whole pancreas may be destroyed and you don't have any production of insulin anymore. So then you have an autoimmune disease. But please be aware, for diagnostics we talk about disease, but in doing so we have to keep in mind that all of us have autoimmunity in their body. Okay. Now, when do we talk about an autoimmune disease? We have applied Koch's postulates for that. Koch was a microbiologist, and he defined some criteria when you talk about an infectious disease. And these criteria you can try to translate for autoimmune diseases. And there are 5 postulates. One of them is that, as I said, the adaptive immune system should be directed to the target organ or tissue. But that is basically only autoimmunity. So if you have an antibody against your pancreas tissue, then you have autoimmunity. But it goes further, and the second thing states that this autoimmune component should also be present within that particular tissue. So, for instance, in this case, in the pancreatic tissue. So that may be either autoreactive T lymphocytes or autoantibodies. Next, you have to show that these autoreactive components are also pathogenic, because the first 2 are just associations. And to show that they are pathogenic, you should transfer them to a healthy individual and see whether this healthy individual also gets the same disease. Now, ethically, that's not very easy, because you cannot say, I take T cells or antibody from a patient and I inject them in a healthy person, because then this person will have the same disease. However, there is an experiment of nature, and especially for autoantibodies, because if a woman has an autoimmune disease and becomes pregnant, the antibodies that may cause this autoimmune disease will be transferred via the placenta to the child, to the unborn child, and may cause autoimmune phenomena in the child. So if the child is born, it may have these phenomena, although it has not completely the disease because it does not produce these antibodies itself. So as soon as these antibodies have disappeared, the child is healthy again. And in most cases, you don't need any therapy for that. So it's rather safe. There are some worse cases, but that works very well for antibodies because antibodies transfer the placenta. But for T cells, it's more difficult. Not only because T cells do not easily cross the placenta, they do, but not a lot. But the other thing is that T cells always recognize the antigen in the context of MHC. You have heard that already, the concept? Okay. So if a T cell with the T cell receptor recognizes the peptide MHC combination, the T cell should be transferred to a person with exactly the same MHC haplotype. And normally that's not so easy to find such a person. So this third postulate is easy to apply for antibodies, but it's rather difficult to apply for T cell mediated diseases. However, the fourth postulate tells us that it should also be possible to immunize animals, and by the autoantigen, so you inject the autoantigen in this animal, and you hope that the animal produces an immune response against this antigen, and if so, it may also develop the same kind of autoimmune disease. And if that works, you can go back to the third postulate, so then you can take the T cells from the animal and inject them in the same kind of animal which is genetically similar. So we call this inbred rats or mice or monkeys. So in that case, if you have an animal model, you can also fulfill the third postulate. And finally, the fifth postulate tells us that to prove that indeed this autoimmune component is responsible for the disease, you should try to cure the disease by getting rid of this autoimmune component. So you can give immunosuppression, so downregulating the immune system, or you can take away, for instance, the antibodies by plasmapheresis whatsoever. And then there should be cure or at least amelioration of the clinical manifestations. So these postulates we normally apply for all kinds of autoimmune diseases. And I will apply them to two examples. I'll do that later on. There are many autoimmune diseases altogether, and as we discussed already, that we like to distinguish all things and we put things in boxes. Also for autoimmune diseases, we like to put things in boxes and we distinguish T cell mediated autoimmune diseases from antibody mediated autoimmune diseases, so where the pathogenic component is different. And we also like to distinguish organ-specific versus systemic autoimmune diseases. So organ-specific will say that the immune response is directed to one tissue only, like in diabetes, or the whole body is affected, like in rheumatoid arthritis or in systemic lupus erythematosus. But as mentioned, all these classifications are arbitrarily given by people, and there is no such definite distinction between T cell and antibody mediated and organ and systemic autoimmune diseases. Altogether, there are people that say that we have about 60 to 100 different types of autoimmune diseases. Some of them are well defined as being autoimmune, others are less well defined. There it's more that we have an autoimmune component in the disease, but as such it's not completely fulfilling the criteria. On top you have myasthenia gravis, which is a disease where the transfer of the signal from the nerve to the muscle is attacked, because the antibodies are directed against the acetylcholine receptor. I will refer to this disease a couple of times. And then you have muscle weakness. I will show you later on that this is a typical autoimmune disease. and then you can go down, and you end up with diseases like atherosclerosis, which some people say is an autoimmune disease, and if you claim that, we have to state that nearly everybody of us has an autoimmune disease, because all people have, to a certain extent, atherosclerosis. However, it's not that simple to say that it's an autoimmune disease. It's more like an autoimmune component within the disease. Anyway, the things in blue behind it are the suspected autoantigens. There are two diseases, inflammatory bowel disease and celiac disease, where you have an antigen in red, which is not a typical self-antigen, because ASCA, in case of the inflammatory bowel disease, means that there are autoantibodies against cerevisia, how do you call it, Saccharomyces cerevisiae, which is Baker's yeast. And in case of celiac disease, it's gliadin, so it's a component within how do you call that, the bread components. Okay, if we now look at myasthenia gravis and try to apply the postulates of Koch, we say that there are indeed antibodies present in the circulation of these patients against the acetylcholine receptor, and as mentioned, this is a receptor on the muscle side, which is important to get the signal from the nerve, and if the signal is not transduced properly, the muscle will not contract, so you have muscle weakness. However, the antibodies are present in the circulation, as mentioned, but it appears that they are also detectable on the neuromuscular end place, so where the transmission of the nerve signal is taking place. So it's on the right location. It's an antibody which is detected, and this antibody indeed can transfer from the mother to the child during pregnancy via the placenta. And these newborn children from mothers with myasthenia gravis also have the clinical manifestations of this disease, so they have the muscle weakness. But as mentioned, these maternal antibodies will disappear because the half-life of IgG is about 3 weeks. So within about 3 months, you have got rid of all these maternal antibodies, and you will cure from the disease spontaneously. You don't need any medication whatsoever. It's possible to immunize animals with the acetylcholine receptor, and then the animals will develop an immune response against the acetylcholine receptor and make antibodies, and these antibodies also in the animals have the same disease phenotype. So they have muscle weakness, etc., etc. And finally, if you remove the autoantibodies from the circulation, you can at least cure is perhaps a difficult word, because later on the antibodies will be produced again by the plasma cells, but at least you can reduce the disease manifestations. So myasthenia gravis is a typical autoantibody mediated autoimmune disease, which definitely is an autoimmune disease because it applies to all the criteria. The other one I want to show you is multiple sclerosis. Multiple sclerosis is a disease of the central nervous system, where we think that the immune system attacks the myelin sheaths from the nerves. And the myelin sheaths are very important for transferring the signals from the body of the neurons to the end of the axons. If you don't have these myelin sheaths, the transfer of the signals is very slow, and so you don't react very fast. Now, if we look in the circulation of patients, we can find T cells that are reactive with components that are present in this myelin sheath. However, if I test all of you, I'm quite confident that I will find these T cells also in your body. Hopefully you don't have multiple sclerosis and you don't develop it, so you don't have to be scared for that. But we all have these T cells. So it's definitely not sufficient to say, okay, I find the cells, so now you have the disease. You have to look into the brain and see whether the T cells indeed have passed the blood-brain barrier. And in healthy persons, the T cells will not pass the blood-brain barrier, so you will not have an attack in your central nervous system from your own immune system. However, in patients, for whatever the reason, the blood-brain barrier is interrupted, and the T cells can enter into the central nervous system and cause disease. So yes, T cells in patients are also present in the lesions where you expect them. As mentioned before, adoptive transfer of T cells from one individual to another is ethically not done, but it's also not easy because you have this MHC restriction you have to take care of. However, we do have animal models, which we call experimental allergic encephalomyelitis. Nowadays we call it experimental autoimmune encephalomyelitis, but originally we thought it was an allergic disease, but later on it appeared to be autoimmune. But anyway, if you immunize animals with all kinds of substances of the myelin sheath, you get a similar kind of disease. And I will not go into detail, but if you now take the T cells from these animals and you inject them in a healthy animal of the same type, genetically identical, then you also induce with the transfer of these T cells the same type of disease, the same type of clinical manifestations. And finally, also, if you suppress T cell reactivity, you can prevent disease manifestations. So basically we say that it's quite sure that multiple sclerosis is an autoimmune disease. We have some trouble in really proving that T cells are responsible because we were not able to transfer it in humans. But nevertheless, we state it's a T cell mediated autoimmune disease. Interestingly, quite recently, one has started therapy in multiple sclerosis where B cells are depleted. And this therapy helps wonderfully well. So somehow B cells are also very important in this disease, although it doesn't mean that the B cells are the pathogenic cells that are the ones that are doing the job within the central nervous system. But they somehow play a central role in inducing the disease. But that's something else. So we have T cell mediated and antibody mediated autoimmune diseases. And now we have the problem that in the laboratory, we have to find a test for diagnostics. And to make it clear, if we think something is a T cell mediated autoimmune disease, we have a problem to develop a test. And the problem is that the reactivity is MHC restricted, which means that for each patient I want to do a test, I depend on a test system that applies the MHC molecules from the patient. And since MHC as such is extremely diverse in the population, I have to design a test for each individual patient, which is rather impossible because I cannot control it, I cannot have normal values. So basically what I want to say is that for T cell mediated autoimmune diseases, I have a problem in diagnostics because there is no test available. The only tests I can do in terms of autoimmunity is detect autoantibodies. And the big advantages of autoantibodies is that the antigen that is recognized, and in this case it's a bacterium, but it may also be an autoantigen, the antigen does not have to be processed like in case of the T cells. So the antibody is able to react with a complete antigen without further putting it in pieces. This doesn't mean that I only can develop diagnostics for antibody-mediated diseases, because it appears that also in T-cell mediated autoimmune diseases, like in diabetes, you also have autoantibodies. It might be as a kind of side effect, which you can use them as a marker for disease. And that's what you have to realize. You analyze the antibodies, the autoantibodies, not by definition because they are pathogenic, but they are just good markers for disease. If albumin, one of the most prominent proteins in the serum, would be a good marker for multiple sclerosis, that would be fine, even if it has nothing to do with the disease at all. But if it discriminates between patients and healthy persons, then you are in a good way. So my issue is that autoimmune diagnostics is about autoantibodies only. You don't test T-cell compartments. Now, what kind of technologies do we have for autoantibody detection? And I will go with you through these 5 technologies. And I will start with immunodiffusion. This is a technology which is not used or hardly used anymore in the laboratories, but it was the basis for all tests which are being used nowadays. And basically they are also, the data that are in the literature about sensitivity and specificity are often based on this technology, not on the new technologies. Immunodiffusion means that you have antigen here and antibody there. And what you do is you make it possible that the antibodies as well as the antigen move towards each other. That may be because of diffusion, just a physiological process. And now you have to realize that antibodies, if you look at antibodies, antibodies have at least two antigen binding sites. And because of that, they can make huge networks, immune complexes, between antigen and antibodies. But it depends on the concentration of the antigen as well as the antibody, what happens. If you have an excess, and that is on the left side, of antibodies, so you have a very little amount of antigen, the antigen will be bound only by 1 or perhaps 2 antibodies. And each antibody binds only 1 antigen. So you will not have huge networks whatsoever. On the other hand, if you have antigen excess, so you have low amounts of antibody, each antibody will bind 2 antigens, but the chance that another antibody binds to one of these antigens which already have bound to another antibody is very small. So again, here you don't have huge immune complexes. Only in the area where you have a kind of equivalence, so that more or less the same amount of antigen in molecular numbers versus antibody, then you have this formation of huge immune complexes where an antibody binds 2 antigens, but each antigen is also bound by another antibody, and so on and so on. And if you make these large immune complexes, they have, not only in the test tube, but also in the body, the nasty thing that they precipitate. So they just go down in a blood vessel, in the skin, or in the kidneys, or in the lungs, and that happens in places where the blood flow is low. So especially in the capillaries, so in the small blood vessels. And that causes a lot of clinical problems if you have autoantibodies and circulating antigen. But what I want to say is that if you do these immunodiffusion assays, you will have precipitation of immune complexes at a certain spot where you have equilibrium between the amount of antibody and antigen. And you can do the following experiments. You have the antigen in this hole, and this is a kind of gel system. So you make 7 holes. Here you put the antigen, then you put patient serum in this one, in that one, and that one. And here you put a control serum, and in this control serum you are sure that a certain antibody is present. And in this control serum, an antibody of course reacted with this antigen. And in this you have, for instance, a negative control where the antibody is not present, or another antibody is present for that. You have multiple possibilities. So now if diffusion starts, the antigen moves towards the patient serum, towards the control serum, and so on. And the sera will also start to diffuse towards the antigen. They also, of course, go outside, but that doesn't matter. And somewhere in between, they meet. So if the antibody against this antigen is present here, Somewhere in the middle, you will have this equilibrium where the amount of antibody is the same as the amount of antigen. And there you have formation of immune complexes, and there they precipitate. And that's what you can see. So what you will see is, for instance, if this is a positive control serum, you see that there will be a line, precipitation line here. If the line develops like this, and here's the positive control and here's the patient, it implies that the patient has exactly the same antibodies towards this antigen as this positive control, because there is this bending of the line, of the curve. If there is such kind of crossing, there are antibodies present against the antigen in the patient as well as in the positive control, but the antibodies are different. They react with a different component of the antigen. And this is what you see in real life. These are the so-called precipitation lines. Sometimes you see two lines, which means that there are two antibodies present in the serum. Sometimes you see only one line. You say that it may cross, which means that there is no identity. You may also see that there is a bending in the curve, which means that there is identity. You see that here better. Or you see that there is no interference with the holes next to it, and then there are only antibodies in this hole reacting with this antigen. So you have multiple possibilities, but as you may understand, reading these tests is extremely difficult. These are beautiful examples, but they may look very nasty. So there is some very subjective part in reading these tests. They are very labor intensive, and that's why people said, okay, we don't like to do it anymore. We like to look for alternatives. And they have been developed in, first of all, we have the so-called indirect immunofluorescence. And if we do indirect immunofluorescence, we take, for instance, tissue sections or cells. You can take both. And you don't take that from a patient, but you can take that from a healthy person or from an animal. And in case of diabetes, for instance, you can take slices of pancreatic tissue. You incubate that with the serum of the patient, and you check if there are autoantibodies present reacting with this tissue. If yes, they will bind. If no, they will not bind. If they do bind, you have to visualize them by adding an anti-human immunoglobulin. So this is an immunoglobulin that is reactive with the human Igs. And this immunoglobulin, for instance, produced in a rabbit or in a goat, is labeled with a fluorescent dye. So on all places where autoantibodies have bound to the tissues, these reagents with the dye also will bind. And if you now look under the microscope, you will see the distribution in tissue of the antibody binding of the patient. If you use cells, you may see different types of patterns. In this case, you look for antibodies against nuclear components, which we call anti-nuclear antibodies. And there it comes up that you have to be able to distinguish all kinds of patterns. So it may be, this is a typical cell line where you have a lot of dividing cells. So this is a dividing cell. And here you can see that all cells are staying positive, and also the dividing cells staying positive. And that's why you call this a homogeneous pattern. Don't bother about the patterns. In this case, you see that only the nucleoli are positive, while in the dividing cells, they are not reacting, which is not strange if you realize that the nucleoli are the production facilities of the ribosomes. And in a dividing cell, there is no ribosomal activity. There is no protein synthesis whatsoever. So you don't need these structures anymore. You also have a so-called centromere pattern, which means that each chromosome, each centromere of each chromosome is being staked. Well, this gives you further information about disease associations, etc., etc. I will not go into detail about that. But you have to realize if you do this test, you have to recognize the pattern and distinguish relevant patterns from irrelevant patterns. specialists can distinguish in these cells about 60 different patterns. I don't know how they do it, I can't, but you have to realize that it's quite specialized job. You also can use, instead of cells, you can use tissues. In this case, it's esophagus, monkey esophagus tissue. And if you have this staining pattern in the smooth muscle area of this tissue, it is associated with endomysium, which is the structure surrounding you can see it here, that the center is black, which is not stained. That is the smooth muscle part, and the tissue surrounding it is stained, and that's what you call endomysium. And these antibodies are very characteristic for celiac disease. So if you see this pattern in the right way, you know that there is a good chance that there is the patient having celiac disease. However, you should realize if you have autoantibodies against smooth muscle cells, you see staining exactly in the same region, but then the staining pattern is reversed, then the center is positive and the surrounding is negative. So you really have to be able to distinguish that, because these smooth muscle cell antibodies are linked to autoimmune hepatitis, a completely different type of disease. Okay. This third test I want to discuss with you is the so-called radioimmunoassay. This was an assay which was used especially in the United States for many, many years. And the next test I will tell you was an ELISA test. You may have heard of that. ELISA tests were predominantly done in Europe. And that is because the patent was in Europe and in the United States, respectively. So the Americans didn't like to do ELISAs, the Europeans didn't like to do radioimmunoassays, although some assays for some diseases were better, but who cares? A radioimmunoassay tells us that, in this case, you have to purify the antigen, you have to radio-label it, so you have to add a radioactive tag to the protein. You keep this still in liquid phase, so in solution, and then you add the serum of the patient, still in liquid phase. If the antibody is present, it will react with the radio-labeled antigen and will form soluble antigen-antibody complexes. And now again you add anti-human immunoglobulin, which is not labeled whatsoever. And this will interact again with these immune complexes to make large immune complexes. And as mentioned, large immune complexes have the tendency to precipitate. So if you spin them down in a centrifuge, you have the radioactivity in the pellet and the free-floating antigen in solution. So the amount of radioactivity in your pellet tells you something about the amount of antibodies which are present in the test serum. If there is a lot of antibody present, you have a lot of radio label in your pellet. If you have a little amount of antibody, autoantibody, all the radio label will remain in solution. So it tells you exactly the amount of antigen. The problem actually is that with this test, you need to be sure that your antigen is very, very pure. Because if it's not pure, you have contaminations. And if the antibodies do not react with the antigen, but with the contaminations, you will also have radio label in your precipitate, and you think it is specific antibody, but it is against which you don't, something you don't know and you don't like. The disease I mentioned before is myasthenia gravis, and for myasthenia gravis, the gold standard for detecting the autoantibodies against the acetylcholine receptor is this radioimmunoassay. But in this test, we have one big advantage, because we don't have to be able to purify the acetylcholine receptor very well. We can just make a muscle extract where the antigen is there, and then we don't label the acetylcholine receptor, but we radio-label alpha-bungarotoxin. And alpha-bungarotoxin is a toxin from a snake. And now you understand probably also why these snakes are toxic, because they bind to the acetylcholine receptor and prevent the signal transduction from nerve to the muscle. So you have muscle weakness, you stop breathing, you stop with your heart beat, etc., etc. But this component, this toxin, has a very high affinity and a very specific affinity for the acetylcholine receptor. So what we do is we radiolabel the toxin, incubate this radiolabeled toxin with a muscle extract, and then the toxin will specifically bind to the acetylcholine receptor. So in that way, I'm sure that I only radiolabel the antigen I want to know. Next, I incubate it with the antibodies from the patient. They may react. I can precipitate it with an anti-immunoglobulin, and the amount of radioactive label is very clearly correlated with the amount of antibodies which are present in the serum. Clear? Okay. Now, as mentioned, the ELISA system is more or less similar as the radio immunoassay, with the only exception that is the test is not performed in liquid phase, but is performed in solid phase, which means the antigen has to be purified, similarly as in the RIA, but now it's sticked to the surface of a plastic well. And then you incubate with the antibody, and the antibody is detected with an anti-human immunoglobulin, with an enzyme, or with a fluorescent dye. Nowadays, you also use fluorescent dyes for that. The disadvantage of this test, as compared to the radioimmunoassay, is that because of the binding of the antigen to the surface of this plastic, the conformation of the antigen may change. And if the conformation of the antigen changes, the result may be that the autoantibody does not recognize the antigen anymore. And that is the big advantage of the radioimmunoassay, because you have the antigen in liquid phase, and the conformation will be the same as in real life, and the antibody is still able to recognize. Now, to circumvent that problem, one has identified, I come back to this one, one has designed some other ELISA systems. One of them is so-called capture ELISA, and in this case the antigen is not directly coated to the surface, but what you coat first is an antibody against the antigen. And next you incubate with the antigen, so now the antigen doesn't bind to the plastic, but it binds to the antibody, and now the conformation of the molecule remains in a good order. That's what we expect. The problem here is, of course, that you use an antibody, and because of using this antibody, you block also one of the epitopes that may be recognized by the antibodies of the patient. So that's why they recently developed a new system, which we call an anchor ELISA. And in this case, the antibody is not captured by an antibody, but the antigen is linked to a small peptide, and the peptide is used for binding it to the plastic. And in that case, you still have the right conformation of the antigen without blocking any of the epitopes of the protein. Go back one slide, because whatever type of ELISA you use, you are still able to quantify the amount of antibodies. As mentioned in the radioimmunoassay, you have the amount of radioactivity which is related to the amount of autoantibodies. In case of ELISA, you have to make a kind of standard curve, and there you have reactivity with increasing amounts of antibodies of known amounts. So that's a kind of international standard where you say, okay, this is, for instance, 1 microgram of autoantibody, this is half, this is quarter of a microgram, etc., etc. From this you make a standard curve, and then you can read all the test results from your patients in this standard curve, so you know that this patient has about this amount of autoantibodies available. Again, also for this test, you have to really purify the antigen, because if you have contamination, you may have false positive results because of antibodies to irrelevant antigens. And the last test I want to show you is a so-called multiplex immunoassay. That is a new device. A multiplex means that you measure more than one component in the same test system. So you measure multiple autoantibodies. And what you do is you have beads, small spheric beads, which are coated with different antigens. So for instance, the blue one is coated with antigen A, the green one with B, and the red one with C. Next, you incubate these beads with the serum, and in the serum you have antibodies against B and against C, but not against A. These antibodies will react with the beads of the right color. You wash, and next you come back with a reagent that detects if antibodies have bound to the beads. And the next step is that you run all these beads through a kind of flow cytometer. And the flow cytometer looks for each bead and looks for two things. First, do antibodies have bound because of this staining? And the second thing is, what kind of bead is it? Is it a red bead, a blue bead, or a green bead? And it stores all these data, and in the end it can tell you that indeed antibodies are present against the red beads, so against antigen C. There are no antigens present against the blue beads, so antigen A, and there are antibodies present against the green beads, antigen B. Right? Go into detail a little bit more. So what you call, this is a so-called Luminex system. You can use the system for many more analytes, not only for autoantibodies. You can use it for cytokines, you can use it for MHC haplotyping, etc., etc. They are all small beads, and they all have exactly the same size. And now you start to dye these beads. You make them. You make a mixture of two dyes. So you make a whole bunch of beads, and one part of the beads you incubate in this bar. So you put in beads, you put in the red dye, the purple dye, and the beads go in, and they will take up this dye, this color, this particular color. It's a little bit light, but you can see here the beads, and it has taken up the color. Now you wash away all the color, and then the bead will shrink and will keep the color inside. In this way, you can make up to, so with these two different dyes, you can make up to 100 different bead colors. Obviously, you have to make them, each color you have to make as a batch separately. But this means that I can do, theoretically, 100 tests, different tests, within one analysis. Because each color I can link with a different type of autoantigen. In this case, I take 4 antigens, SSA, SSB, SCL70, and bovine serum albumin as a kind of control. It doesn't matter what this means, but just to show the system. And I mix these beads and put them in a microtiter plate. So all different colors are there, and also in all the other wells. Then within each well, I incubate with a serum of the patient, and if there is an antibody there, it will bind, for instance, with this bead. I have a detection reagent, as I mentioned in the beginning. There is no antibody against these beads whatsoever. Then I run the beads through a flow cytometer, and they will be hit by 2 lasers, the red dye laser and the green laser. And you can distinguish each bead separately. You have had the principle of flow cytometry already? Okay. So basically, if you use it for cells, which is normally done, it's exactly the same as we're using for these beads, although the beads are much smaller. But you can regulate the system so that each bead of every single bead passes this nozzle at a single time, and no double beads are passing. Now what you do first then with the green laser is that you identify the amount of reporter on the surface. So that means the amount of antibody, autoantibody that has bound to this bead. And second, you try to identify which kind of bead type you have. Is it the SSA bead or is it the SSB bead? And then of course you know, basically from all these 100 different beads, all at once, if a patient has antibodies, autoantibodies to any of these kind of autoantigens. And theoretically that sounds very nice because, as I mentioned, we have about 60 to 80 autoimmune diseases. So if I could identify an autoantigen for each autoimmune disease, I would be ready with one simple test and would have checked the patient for all these autoimmune diseases. But what I will tell you in the next part is that you have to deal with false positives and false negatives. And that is a big challenge because if I do all these tests and a patient is suspected for having diabetes, and then I find an autoantibody which is associated with multiple sclerosis, what should I do? Should I tell it as a laboratory specialist? Should I tell it the clinician because he didn't ask for it? If I tell it the clinician, should he start all extensive research to find out whether there is any clinical manifestation of MS, which is quite expensive, of course? Should we tell the patient that perhaps in the future he may develop a disease? So ethically, it's a very difficult thing to deal with, but technically, as I mentioned, it is possible. So from here, this is the test, the test system. Is that clear for you? So now you have done the test and the result is positive or negative. And what can you do with that? And this is basically statistics, but you should also try to think what a clinician has to do with the test results. Basically, you have the situation that you have a test which may be either positive or negative. To make it complicated, you may also have something in between, because somewhere you're not sure if it's positive or negative, but we don't talk about that. And you have a patient which is having the disease or is not having the disease. The clinician doesn't know, but obviously somehow the patient should have the disease or not. Now, if the test is positive in a patient that has a disease, we call it true positive. If it's positive in a patient that does not have the disease, we call it false positive. If the test is negative in a patient that has the disease, it's false negative. And if the test is negative and the disease is not there, it's true negative. So basically we want a test that has a high number here and has 0 here. But I can tell you that that test does not exist. So now, the things that are most often used in literature is the terminology sensitivity and specificity. So can anybody of you tell me what, in simple words, what does it mean, sensitivity?
The amount of positives in people that do have the disease.
Right. So the percentage of positives within the population having the disease. And if you then, you can make formulas from that, you can calculate, you can say it's the true positives divided by all positives, it's the true positives divided by the true positives plus the false negatives, but whatever. But it's, yeah, but whatever is not the right word because it's as it is here. But it's correctly said that it's the percentage of patients having a positive test. What means specificity then? That's just the other way around. So that means the percentage negative tests within the population that does not have the disease. Meaning, it's the true negatives divided by the true negatives plus the false positives. Okay. Now, sensitivity and specificity should be defined based on patients versus non-patients. In many experiments in literature, the non-patients are healthy controls. But to distinguish a patient from a healthy control, you don't need a test. You don't even need a clinician, because everybody more or less knows from himself, am I healthy or am I sick? Because otherwise you don't go to the clinician. So the problem is to distinguish a patient having the disease from a patient with another disease with similar manifestations. That is much more difficult. And that is a control situation that you really should use when you define false positive, true positive, and so on. Not the health controls. There the test will also do very well. Okay, then of course, when do I call a test positive and when do I call a test negative? That's not so easy because you have to define a cutoff. It's easy if I have test results like this. So this is the signal of the test. This is the patient population. This is the control population. If all patients are positive and all controls are negative, I only have true positives and true negatives. That's the ideal situation. I can put the cutoff right in between. If I have this situation, that I have no distinction between the signal of the test, between the patients and the controls, I have a lousy test. Because the test will never distinguish between patient and controls. Whatever I do is cut off. In reality, it's like this. There is overlap between the patients and the controls. And I can choose to put a cutoff such that I have 100% sensitivity, because all patients are positive, or I can choose 100% specificity, where all controls are negative, or something in between. The choice I make is heavily dependent on the type of therapy that I need. If I need a therapy which is very safe, like an aspirin, I can make the choice that to put the cutoff low. This means that I will treat some patients which do not have the disease with a medication which is not very dangerous. I take that risk. But at least I treat all patients. But if the treatment is kind of cancer therapy, I have to be careful that I do not overtreat the patients that do not have the disease. And there it's safer to put the cutoff high and accept that some patients are missed, will not get the diagnosis, and will not get the right treatment. But here I want to prevent that the patients, that the non-patients are overtreated. And of course you can choose something in between if you don't know what the treatment really will do. To have a really objective way of defining the cutoff, you can make a so-called receiver operating curve. That is put here. And the receiver operating curve means that you take multiple cutoff values, and for each distinct cutoff value, you calculate sensitivity and specificity. And you put these on the y-axis as sensitivity, and on the x-axis as 1 minus the specificity, so the inverse specificity. If you do that, you get a curve like this, and the closer you get to this point, the closer you get to the optimal test, because here you have 100% sensitivity and 100%, because this is reversed, 100% specificity. So this is the ideal situation. This is a bad situation. Here you have 100% sensitivity with 0% specificity. and here you have 0% sensitivity and 100% specificity. Yeah? So from this you can objectively calculate the point which is most close to this, and basically you can also calculate the area under the curve. If the area under the curve comes close to 1, you have a good test. If the area under the curve comes close to 0.5, 0.5, you have a lousy test, because there you don't discriminate between patient and health control or disease control. Is that clear? Now we have a problem that we have defined sensitivity and specificity, which is useful in literature to compare tests, but the clinician has in front of him only one patient. And now the result is positive. What do you do? Can you calculate from sensitivity, specificity, the value of a positive test result for a single patient in front of you? It appears very difficult, and the stuff is difficult anyway, because clinicians are having much difficulty with doing this. If you give clinicians the test result together with sensitivity and specificity, they cannot calculate what the result will be for the single patient. There is another way to do it, that's positive and negative predictive value. Can somebody describe what positive predictive value means?
The diseased amongst all positives.
Yeah, right. It's the amount of, so the percentage of real patients within the positive results. So I have one patient in front of me, and I know the positive predictive value is, for instance, 80%. Then I know that this patient has 80% chance that it is indeed a true positive result, but still 20% chance that it's true, that it's a false positive result. That I have to take care of. Similarly, a negative predictive value, which means the amount of, so the percentage of control patients or healthy individuals within the total amount of negative test results. There is a link between sensitivity and specificity. If sensitivity is high, normally the negative predictive value will be high. If specificity is high, normally the positive predictive value will be high. The problem here from this issue is again that clinicians cannot work with these items. And one of the problems here is that these values are dependent on the prevalence of the disease. And don't think of this just to show you that if you put the formulas in a different way, you find that prevalence, so how often does the disease occur, is within this formula multiple times. And now you have to realize that we are talking about autoimmune diseases, and autoimmune diseases are very rare diseases. So some autoimmune diseases have a yearly incidence of 1 in 10,000. So if I test 10,000 people and I have a specificity of 99%, how many false positives will I get? Then I have 10,000 patients to test, and I have a specificity of 99%. So I have 1% false positives, it's 100 false positives, right? If I test 10,000 people and the sensitivity is 100%, how many true positives do I have? One. So altogether within these 10,000 people, I have 101 positive results, And from these 101 positive results, I have to find out who is the patient, which is a terrible job. So, there's another way to put this clear. This is an example of celiac disease. Celiac disease is, by definition, not a real autoimmune disease, but nevertheless, we do have autoantibodies against this tissue transcriptaminase. Don't remember that, but celiac disease is one of the most common autoimmune diseases, meaning that about 1 in every 200 people is having the disease. So again, if I start a calculation, the prevalence is 0.5%. So I go for a sensitivity of 97% and a specificity of 98%. And then I can calculate the positive predicted value. So for instance, if I take 200 patients, I will have, with a specificity of 98%, I will have 4 false positives. With a prevalence of 0.5, I will have 1 true positive. So from each 5 positive results, 1 is having the disease, 4 are not. So about 20% is my positive predicted value if I check the whole population. Negative predicted value is rather good because if the sensitivity is high, that's 100%. Now, if I go to the first line clinical, so the general practitioner, there we can calculate that about not half of the people have the disease, but about 3% of the people have the disease, because as I mentioned, only people that have complaints will go to the clinician. So people suspected of having celiac disease will show up, and altogether 3% of the general practitioner population appears to have celiac disease, although 3% of the ones that show up with the complaints fitting with it. Now, if I now test 100 persons, I will have 2 false positives, and I will have 3 true positives. So now my positive predicted value clearly increases up to 60%. And I can make it even better if I say, okay, if there is a patient in the family with celiac disease, I already have chance that the other family member has 10% chance of having the disease. So then again, I can further increase the positive predictive value up to nearly 85%. So what I want to show you that indeed, that depending on the type of population coming to you as a clinician, will influence the positive predictive value. So again, this implies that a clinician is not very much helped by giving positive or negative predictive value. You should go one step further, and then you go to likelihood ratios. And again, here you have likelihood ratios for positive results, and you have likelihood ratios for negative results. Likelihood ratio for positive results is the same as sensitivity divided by the reverse of the specificity. So 1 minus specificity. And the negative likelihood ratio is specificity divided by 1 minus the sensitivity. Don't try to replicate all these formulas. Try to replicate the way of thinking. Now, what can you do with a positive and a negative likelihood ratio? If a positive likelihood ratio is above 10, or a negative likelihood ratio is below 0.1, you have a test result which is clinically very significant. If the test result is between 5 and 10, or 0.1 and 0.2 for a negative, it's a modest clinical effect. And it goes further down if the values drop or increase. And I really challenge you to ask in the coming lectures the lecturers what the likelihood ratios are of their test systems. So people come up, as I heard in the introduction, they develop beautiful new tests. And then they show up with specificity of 95%, which sounds reasonably good. In clinical practice, that is a lousy test. If you go to likelihood ratio with a specificity of 95%, you lose. You will never come to the market with that product. So try to be critical in the data that people give you. And challenge, ask for likelihood ratios, and I'll show you why. Because if you know likelihood ratios, you can calculate the transition from pre-test probability of having a disease to post-test probability of having a disease. Meaning that if I have a chance, based on clinical manifestation, that a patient has a certain disease of 10%, and next I find a positive test results with a likelihood ratio here in the middle of 10, which is good, I end up with a post-test probability of having disease of 60%. So if I increase the chance of having the disease in this single patient from 10 to 60%, which is a lot. I'm not there, I'm not yet ready. I have to find other clues to find the final diagnosis, but this is a huge increase. If, however, the likelihood ratio is only 5, it's still usable because I go from 10 to 40%. And if I have a likelihood ratio of 2, I only increase from 10 to 25%, which is not a lot. So I still have a lot of uncertainty about the final diagnosis. And you can put it the other way around. If you have a negative test result, if I start with a pre-test probability of 10%, and I have a negative likelihood ratio of smaller than 0.1 of my test system, I end up with a chance of less than 1% that this patient still has this typical disease. Well, it's rather safe. Okay, I'll see what happens, and depending on the type of disease, of course, but it's not just that. If the negative likelihood ratio increases, you can see that also the chances are less good, because if I go from 10% to something like 4%, what is my gain? Why did I do this test? What does it help me? This likelihood ratio might have helped me with a pre-test probability of 80, but not with a pre-test probability of 10. But anyway, what I want to say is that in this case, if I report my data as being positive together with a likelihood ratio, the clinician is able to calculate for a single patient what the result of the test means. And I have that in this slide for a certain type of disease, doesn't matter what. But here again you have the pre-test probability, so that is based on the clinical manifestations. And this is the post-test probability, which is based on the combination of clinical manifestations together with test result. And in this case, this is a renal disease. So you have glomerulonephritis. There you have 53% chance that you have the disease based on clinical manifestation only. And now if I have a test positive, I have a chance of 99%. And if you realize that this disease needs to be treated with cyclophosphamide, which is a very toxic drug, you understand that you have to be sure. And 99% is pretty sure. However, if the test is negative, I still have 15% chance of having the disease. So I'm not completely excluded. I need to find more evidence. On the other hand, if the patient shows up with a very minor manifestation, which is chronic sinusitis, I have a pre-test chance of only 1%. If I now have a positive test result, I come up with about 40%. Now, this presentation will not be treated with a cyclophosphamide, but just with a milder drug. But nevertheless, this 40% is far insufficient to make a diagnosis. So, what I want to show you here is that by putting likelihood ratios in these kind of graphs, linking pre-test probability to post-test probability, the clinician will be able to calculate the test result effect of each individual patient, and the only thing he needs to know is the way to calculate the pre-test probability. He should know some epidemiology. And then I come to the end. You want to start? Sorry. This is my last slide. So realize that auto-antibody detection uses many different technologies, but that the optimal test does not exist, and therefore you need these statistics to treat the data, especially in autoimmune diseases, which are rare diseases.